Jai Hind everyone. My name is Gunjan Saxena, Assistant Professor Ajay Kumar Garg Engineering College, CSC Department. Today I am here to continue with the DA series. In this particular lecture, I am just taking a topic, binomial heap, which comes from second unit. Let's start. In this particular lecture, what we are doing, we are just briefing about the binomial tree. After then, we are discussing about the properties of this particular binomial tree. After that, introduction about the binomial heap. Then, the properties belong to binomial heap. And after that, operation of binomial heap. Then, the operation, the name is union in binomial heap. So, first of all, what is binomial tree? In a binomial heap, there is so many collection of trees, or we can say the collection of binomial tree. First, we know about what is binomial tree. So, binomial tree which is represented as BK, which represent the ordered tree recursively. The binomial tree B0 has one node, as so on we can say binomial 1 can having 2. In the next slide, I am discussing what is the process, what is the ordering standard of binomial tree. The binomial tree BK consists of two binomial trees BK minus 1, and they are connected such that the root of one tree is the leftmost child of the other tree. So, suppose this is the representation of B0. As I am discussed, in B0, we are having only one node, and in the last slide, we have discussed if we are making any BK tree, then BK having two particular nodes of BK minus 1. Suppose we are making the B1 here, the value of K which is 1. So, we are creating the tree which is having order 1, that means B1. So, in B1, we are having BK minus 1, where the value of K is 1. So, 1 minus 1 which is 0. So, we can say in the B1 ordered tree, we have two B0 tree. And as we know, B0 having only node, that means B1. What is B1? B1 is the combination of two B0 nodes. And what is the way of connecting these two B0? B0 and having another B0 is the leftmost child. Let's have a look about the B2. If we are making a B2 tree, that means here the value of K. What is the value of K? K is 2. Then in B2 having two binomial heap tree which having the level of BK minus 1, that means 2 minus 1 means B1. B2 is creating by using two binomial 1 tree. What is the process? Process is one is B1 here, and the second one B1 is the leftmost child of this particular B1 tree. So, similarly, we can construct B3. B3 is the combination of two B2. B2 is, this is the representation. What about B4? B4 is the collection of two B3 nodes. This is one B3 and this is another B3. I hope you are understanding how we are going to create a binomial ordered tree. Next, there are some properties which every binomial tree have to satisfied. You know, first one is BK has 2 to the power K node. What does that means? Let's in the next slide, one by one, I am solving, or we can say we can going to prove all these particular properties. Let's have a look. What is the second one? BK. Every BK tree has height of K. Third one, for ith depth from 0 to K, BK has exactly Ki node at every depth, or we can say at the ith depth. What we are saying, every ith depth has particular K node. Fourth one, the root of BK has degree K and all other nodes in BK have a smaller degree than K. What was the fifth one? Fifth one is, if k, the value of k is greater than or equal to 1, then the children of the root of bk are in the particular form, or we can say in the order like bk minus 1, bk minus 2, bk minus 3 up to b base 0 from left to right. Now, let's prove all these 5 properties one by one. So, what the first property is saying, every bk has 2 to the power k nodes. So, let's look at here. 2 to the power k. What does that means? If we are saying about B4, the balanced tree, the binomial tree at 4th level, or we can say B4. So, 2 to the power 4, here the value of k is 4, 2 to the power 4. The value of 2 to the power is 16. That means in B4 binomial tree, there are exactly 16 nodes. Okay, so this is the proof of the first property. So the value is 16, and have a look about the B4 tree, and this particular tree having exactly 16 nodes. What about second? Second one is saying bk has height k. If we are thinking about the B3, so this is the representation of B3. As we know the tree structure, which is starting from level 0, 0, 1, 2, 3. So then the height basically is the number of level. So B3 having level 3, the depth of ith depth, which is level 3. So we can say the bk has kth height, or we can say B3 has level 3 height. In the third property, what we are saying, at every depth I having the exactly node ki. This is the permutation formula. By using kci equals to k factorial upon I factorial k minus I ka factorial, we can calculate these particular values. At the level of 0, we are having only one node. At level 1, we are having exactly 3 node, at level 2 exactly 3 node, and level 3 having 1 node. If we are adding all the particular node, as we know from the property number 1, every bk having 2 to the power k values nodes, so which is equal to 8. And in the fourth property, what we are saying, the root of bk has degree k, and all the other nodes in bk have degree smaller than k. Suppose we are having a node at level 0, and the subordinate, or we can say the child of this particular node having the degree which is always lesser than this particular parent node. As we see, the trees are coming from this particular node, or we can say the degree of this particular node is 3, and every node having exactly less degree of this particular node. Okay. In the fifth property, what we are saying, if k is greater than or equal to 1, if the value of k, we are saying the value of k, here the value of k is 4, then the children of root, all these children, having a particular order which is from left to right, what we are saying, we are thinking about the value of k. As we know, the value of k is 4, having this particular way, bk minus 1, bk minus 2, bk minus 3 up to bk minus 4. If we are putting the value of k, then this particular situation arises. So these are the proof of all the 5 properties which is belonging from bk, or we can say binomial tree. Let's start with binomial heap. What is binomial heap? Binomial heap is a collection of binomial tree that satisfies all the binomial heap properties. What are those? No two binomial tree in the collection of the binomial heap are having same size. What we are saying, if we are making a binomial heap, in this particular heap, no similar type of bk tree are performed, or we can say are formed. Each node in each tree has a key, every value having the key. Each binomial tree in the collection of heap ordered in the sense that each non-root has a key strictly less than the key of the parents. That means it is exactly follows a min-heap property. Okay. Now, these are the implementation area. if we are going to implement this particular binomial heap, what are the field, or we can say the node having which type of attributes? First one is parent, second one is child. Always remember there is a concept of child which is always leftmost child. Okay, now sibling, degree and the key. Roots of the trees are connected using the linked list. What kind of data structure we are using in the implementation, which is linked list. So this is the linked representation, or we can say binomial heap implementation. Suppose this is the example. If we are having a binomial heap having two binomial tree, as we are seeing, this is the B0 heap and this is the B2 heap. So what is the representation? As we discussed earlier about the attributes, what are the attributes? This is representing about the parent, and this is the key value, and this is the degree, or we can say this is the child value, and this is the leftmost child. Okay, so this is the nothing but just a representation, a link representation about the any binomial heap. So what is the example? There is very important question in your university exam. There is a question, they can say a binomial heap having n equals to 13 node. What is the representation, or we can say what are the minimum tree which are forming the binomial heap having exactly n equals to 13 nodes. Okay, so what is the way? First we have to calculate the binary representation of 13, which is 1101. So now what is the representation? As we know, in the binomial, or we can say the binary situation, this is the phenomena 0, 1, 2, 3, which is representing the number of binomial ordered tree which are using to making the heap, which is having exactly 13 nodes. Then what was that? So first one we are seeing the zeroth, or we can say the order of 0 is 1. That means we are using B of 0. At the one place which is 0, that means V1 we are not considering. And in this particular B2, what we are saying, the order of B2 is considering, and the order of 3 which is also considering. That means what is the means, or we can say what is the what is the proof of this particular question ki exactly 13 nodes heap, what kind of binomial heap, what kind of binomial trees are required to create a binomial heap which is having exactly 13 nodes. So these are the random values. We are just thinking, or we can say we are proving these particular B0, B2 and this particular B3 are combining, creating a binomial heap which is having exactly 13 nodes. So remember, this type of questions are very, very important for your university, exactly in AKTU university, Now, this is the another algorithm, or we can say another lemma, which is also important, exactly in our 2-3 marks, mostly asked in your university examination. What was that? N-node binomial heap consists of at most log base 2n plus 1, which is the floor value, binomial trees, because binomial representation of n has floor value of log base 2n plus 1 bits. That means if we are thinking a case having n equals to 13, we know 3 nodes as we have proved earlier. Here the log 13 value, what we are saying, the value of n here 13, which is 3.1, or we can say the floor value 3, we are taking the floor value, the point value is discarded. So 3 plus 1, 4. That means at most 4 tree we are requiring to creating a binomial heap which are having exactly n equals to 13 values, and so on. You can calculate all these 2 values. Now, these are some operations like creation of a new heap. We can search a minimum key in the binomial heap, or we can unite 2 binomial heap. And in this particular lecture, we are discussing about the uniting 2 binomial heaps. And the next one is insertion of the node, removal of the root of the tree, decreasing key, and removal of the node. So these are some various operations which are belonging from the binomial heap, but in this particular lecture we are going to discuss about the uniting two binomial heap. But initially, or we can say first we have to know about how we are going to create, or we can say make a binomial heap. So first we have to, or we can say, allocate a head, or basically this head is initially null, and we are just returning this particular pointer for just starting for the binomial heap exactly, or we can say we are just making a null binomial heap. Okay. So what is the process, what is the phenomena of uniting two binomial heap, or we can say union of two binomial heap? There are two steps which we are discussing. First, we have to procedure repeatedly link binomial tree whose root having the same degree. Okay, what is the process of linking? Basically, in the procedure of linking bk-1 tree rooted at node y to the bk-1 tree rooted at node z, it makes z as a parent of y. Node z becomes the root of bk tree. What are the four different cases which are belonging from when we are uniting? Just go through this particular slide. I am just giving you a gist about this particular cases. What we are saying, there are four major cases. Actually, two cases are there. Just two are depending on the other one. So what we are saying, if we are uniting the two binomial heap, then maybe the first binomial tree having a degree which is not equal to second one, then what we are doing, we are just simply move forward to the list. Pointer just move forward to one place. In the case number 2, what we are doing, if all the three, the first element, second and third, we can say if the first element is x, then we are saying the degree of x and the degree of next of x and degree of sibling of next of x, all three are equal. What we are doing, we simply just move forward the root list, or we can say pointer will go to the forwarding direction. What are the case 3 and 4 which are important? What we can do if the degree of x which is equal to the degree of next of x and not equal to the degree of sibling of x. We are just doing the link, and what is the criteria of linking? As we know, in the binomial heap we are following the min-heap property. Then obviously the root node having the lesser key, and then which one having the greater key is going to the leftmost child. And similarly in the case 4, if the key of next of x is small, obviously the root becomes next of x. Okay, so let's take an example, or we can say previously as we discuss about the linking, what is the algorithm, what is the chunk of code of this particular link. Suppose we are having two trees and the roots are y and z, and initially we are saying this particular z is the parent of y. Basically the y is the child of z. What we are doing, the child of z becomes a sibling of y, and now y becomes child of z. And what is the degree of z when the child of z is increases by the y? Obviously the degree of z will be increases. Now let us take an example. What we are doing, what is the phenomena of uniting the two binomial heap? As we are seeing, these are the two binomial heap which are separately making by using the binomial heap property, binomial making property. So this is the heap 1 and this is the heap 2. We are just unite them. What are the steps? Just simply add the root list. These steps. So we are doing, we are just simply adding these particular root list. So I am just putting the degree wise. Okay, so 2, there is no matter, you can put 3 firstly and 2 secondly, there is no matter. But what is important, we need to merge the root list according to the ordered. Okay, so first one we have to put all the B0, then B1, then B2, if we are having B3, B4 and so on. What we are doing now, pointer is pointing to the x, which is next of x, and this is sibling of next of x. Okay, so now just checking what kind of case is arises. So case is basically the degree of x is equal to degree of next of x, which is not equal to sibling of next of x. What was the case? So as we are saying, this is the case number 3 or maybe case number 4. We are just taking a view which case arises. We know the case number 3 or maybe a case number 4 is going to be because the degree of x which is equal to degree of next of x, and the third degree is not equal. So which case is smaller is going to be a root exactly. So what was that? We are just simply saying, we are just cutting this and the greater child becomes the root. Okay. Now just pointer refresh. First we have to now this is not our next of x now. This is next of x and this is sibling of next of x. Simply just saying. Now what kind of case is there? So case number 2 is here. What was that? In case number 2, simply the degree of x which is equal to degree of next of x and which is equal to degree of sibling of x. What is the solution? Solution is exactly, we are simply said, we are going to just move a pointer forward. Now this is x, this is next of x and this is sibling of next of x. Just check again what kind of, or we can say what type of cases arises. So x having degree 1, next of x having degree 1 and sibling of next of x having degree 2. So the case third or maybe fourth arises when 2 are having same kind of degree and third one having a different degree. So what we are doing? We are just doing the linking process. What was that? Which one having a greatest key is becoming a leftmost child. So simply this is the thing, and we know now this is x, this is next of x and this is sibling of next of x. Now just see. So x having degree 2, nx having degree 2, s and x having degree null. Again case number 2 or maybe case number 3 or case number 4 is arises. What was that? Just linking two particular nodes and go so on. So what was that? So simply this 4, this is the root list and this 4 is the leftmost child. So I am just creating a fresh one. This is the exactly a new, 1, this is 12, this is 10, this is 15, this is 4, this is 9, 11 and this is 20. Now here x, now x is here and x is at null. When our nx having a null value, so the algorithm is going to be stopped. Okay, so this is the proof of this particular two merge, and here 1 2 3 4 5 6 7 8 9 10, the node equals to 10 and we can prove that 1 0 1 0 b1 and b3 we are using, or we can say for making n equals to 10 node, we have exactly two binary tree which are ordered b1 and b2, sorry b3. So this is the proof. Here a 1 bk, or we can say one tree which is b1 and another one which is b3. Okay, so this is how we are going to unite two binomial heap. So, just a wish, or we can say just a recap, a sum up of this particular lecture. In this particular lecture, we are just going to go through about the binomial tree, and after that we discussing about the binomial tree property, what are the necessary 5 properties which have to prove by every binomial tree. After that we discuss about the binomial heap. After that, the 2 main properties of binomial heap, that was no same type of decay order tree present in the binomial heap. After that, we are discussing about so many operations, and in today's lecture we are just discussing about the uniting 2 binomial heap. In our next lecture we are taking some another operation. So okay, Jai Hind everyone.